Okay, good. So last Monday we concluded by finding the meaning of the Coriolis force, the effect of the Coriolis force on the equation of motion. Today we will move and we try to finalize the definition of the equations that will govern our fluid. So we will going to have about 2 hours more or less, okay, up to 10 to 4 more or less. So are you ready? With coffee? Okay, maybe we can make some short break. Okay, so we are going to define, okay, this is the model that we saw last time about the Coriolis force. That one is Coriolis or Corioli. And just to finish, this is the Coriolis rotating platform, which is a very interesting infrastructure staying in Grenoble in France. So it's about 13 meters of diameter. So if you have an idea of making some GFD experiment, you can apply for this. They will give you support and hours, let's say, energy. There will be one man like this, or one woman, I don't know, who will help you to put your experiment. So applications are free and you can apply. So it's very interesting. And I think it's the one in Europe, or yes, I think it's the only one in Europe. Maybe there is one similar in the US. Okay, so now we have to define a little bit better our frame of reference. So even if we said last time that the centrifugal acceleration creates a sort of flattening, so the shape of our Earth actually is elliptical, not perfectly spherical, it's something that we can use as we can consider an approximation and define and take as a sphere as the shape of our Earth. So maybe you already know that we want to consider the frame of reference of a specific point of this over the surface of the Earth, which we have the x-axis directed eastward, the y-axis directed northward, and the z-axis, which is parallel to the radius, so from the ground to the top, okay, perpendicular. So we can define, if this is the, let's say a section, a quarter of our Earth. So if we are more or less here, 45 degrees, it's the latitude of Trieste, more or less. So let's see here. So this is Z, this is Y, and X is in this direction, okay? This is the radius of the Earth, and we can also use phi to define the latitude. So our background rotation, omega, of course can be moved here. Yeah.
You said x is toward, why is it like this?
Because we are going in this direction. So if I'm here, north is here, west is here, and east is here.
Okay.
Okay? So like from here, Greenwich, we are going eastward, we are going westward, we are going north or south. Okay. So our omega has now 2 components, right? So before, when we did the very easy case of a rotating table, the omega has just one single component, which was the vertical one, okay? So if we consider x, y, and z, right? So here we are having a curved reference, and of course we can, if we look at a very short, small scale, we can even, let's say, approximate when this distance here, this scale here is much smaller than the radius, okay? We can consider this and take this area like a plane, okay? But still, our rotation vector will have two components, one on the z and one on the y. So omega, capital Omega, will be 0, omega y, and omega z. And in particular, omega y, so since this is phi, and this is phi, okay, the latitude. So omega y will be omega, because it's the value of the magnitude of this vector, cosine phi, and omega z will be omega sine phi. Okay? So when we have our Coriolis force component, when we do the vector product, remember that in this case we had like yi, j, k, 0, 0, omega, u, v, and 0. Okay? Now we have I, j, k, then we have 0, omega y, omega z, and then we have full 3-dimensional velocities component. So if we play a little bit and we calculate this, what we obtain will be du dt, dv dt, dw dt, and then we will have the first term, which will be I, so this and this, so we'll have plus 2 omega y w's minus 2 omega z v. Sorry. So plus 2 omega y w minus 2 omega z v. Here we have, this is 0 and this is minus with plus 2 omega z u, and here you will have the last one, which will be minus 2 omega y u. So omega y, omega z are this one. So we can define, since we put, if we can put a factor 2 here. Okay, so this is defined as f, which is the Coriolis parameter, which is exactly, let's say, just by a difference of a sinus, which is the dependence on the latitude. It was the same value that we had before, okay? Because we had before, in the simple case, we had just omega z, and we have, you remember, f equal to omega, no? It was the frequency of rotation. While this one, we call it f star, which is called also reciprocal Coriolis parameter. So the Coriolis parameter change as the sign of the latitude. So it will be maximum at the pole, where phi is 90, and 0 at the equator. Okay? So at 45 degrees, they are the same. Okay, so we can also change here and put So where we had F star, F, F, F star. Okay, so we can still reconsider our case of no forces. So we just consider no any kind of forces applied to our equations. And what we obtain is exactly the same result that we had before. The only difference is that in the first case we had that the period of the oscillation was 2 pi over f. Here is 2 pi over f still, but f is 2 omega sin phi, which is pi over omega sin phi. So these, which are like, you remember, the solution of this motion are circular path. So they are called inertial oscillation. Okay? So this is the first and the most basic and the simplest case, let's say the zero approximation for the Navier-Stokes equation in GFD framework. Okay? So we do not have wind, pressure, heat fluxes, nothing. We just have a parcel of fluid which is simply in quiet, over which only the Coriolis force is acting. Okay? And what we obtain is the internal inertial oscillation. So inertial oscillation will have a period, which is the inertial period, which will be, so we can write TO. So the period of inertial oscillation. So when we are at the poles, so this is 1. So we have pi over sigma. But how much is pi over sigma? So write it here. So we know that the period of rotation is 2 pi over sigma. Okay? So pi over sigma is half of the period of oscillation. So this means it is how much? TR by 2, yes, which is how many hours? 12 hours. Don't be shy. 12 hours. And what happened at the equator? This is 0.
So you finish.
Mathematician, please help us. Right. So of course it's yeah. You're lost.
Yes, from TIO. What is T raised by IO? Yes, from
This
there.
is IO stands for inertial oscillation.
Okay.
Okay. So this is exactly what we did before from the simple case of the rotating table. The only difference that the F here now is 2 pi sin phi. Okay, so before we just have 2 pi, 2 omega. Now we have the dependence of the latitude. So the period is dependent on the latitude. Okay, so we can have the spectrum of values of this inertial oscillation. So the period is between 12 hours, the minimum. You cannot have less than 12-hour period at the poles, and infinite, exactly at the equator. Of course, it will be much larger in the proximity of the equator.
My question is, in calculating the period, why did you consider the z component of the diagram?
Ah, you mean why I didn't use this? Because it's exactly the same when I took from here, I had to consider the z component. So the z component is this one, okay? So it's exactly because this if you solve this exactly with this one, with respect to this, the only importance component is the z one, okay? Okay, so it's quite difficult to observe inertial oscillation, but it has been done in the past. So this is one of the few, I think, example that you can find. This is taken, of course, from the Cushman book. So this was evidence of inertial oscillation in the Baltic Sea in the 1936. So this plot is a progressive vector diagram constructed by successive addition of velocity measurement at a fixed location. So I'm fixed and I measure the velocity of the current. The current, let's say, there is no current, but there is something which is moving. Okay, so you may think that a Baltic Sea is very stable, usually very, very calm. So, but when they have storm, but usually it's quite calm. Okay, so if you don't have no wind, no major current, nothing, what you can have, you can really take for weak or uniform velocity this curve, approximate the trajectory that a particle starting at the point of observation would have followed during the period of observation. Okay, and so this is 1, 2, 3, 4, blah 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 blah, and the numbers indicate the dates of the month, 18, 19, 20, 21, 22, 23, 24. And if we calculate the value 2 pi over f, which is this period, it is 14 hours, which is exactly what you have at that latitude of about 58 latitude.
I'm a bit confused. What do you mean by inertial oscillation in the ocean?
So if you are, you can put like drifter, okay? So you can put something which is floating in the sea. You put this. There is no wind. There is no major pressure. So the only thing that you can observe is like this drifting object is in quiet. The only force which is apparent that this object is feeling is the Coriolis force. So the only fact that you are having, in the equation of motion, is this one. If you would be in an inertial frame of reference, of course, this wouldn't be exist. So if you are outside from your planet, from our planet, and you look at that drifting object, you will see that the object will rotate, and that's all. But since we are inside, we will, like in the people from the video, no, which were playing with the ball, the apparent velocity, the apparent motion, let's say, that the drifting object is experiencing is rotating a circular path. Okay, and this circular path, as any circular path, has a period, has a diameter, has a velocity, all the things that we found mounted. And in this case, the most important parameter is the period. Okay, so now we can move more and see what happened when we add all the other terms to our equations. So you remember that we started by it's like this and this, for example. Okay. So this was the Navier-Stokes equation in inertial frame of reference. Then we added the Coriolis force.
F divided by
Sorry?
the F divided by rho density.
This one?
Yes.
Yes, it's okay. It's just a general This is general for surface forces. This is general for body forces. Okay. Yeah, you're right. Of course, we can also like this, like. Okay? But, and in any case, it's important that we know what we are talking about. So now we want to express this, taking in consideration all the three components. So we already started with this one. So then we can have, so 1 over rho minus 1 over rho minus 1 over rho. Then we have the pressure gradient. So dxp. Oh, bless you. Okay, we can close. I don't want to be. I don't know which is the healthiest situation with all the bacteria floating on our head or with the cold wind. Okay. So this is P. Then, if you remember, we have the stress tensors. Over the three component. And then so I will put like okay. So this form here, apart from the Coriolis force, you should already have been done it in the previous part of the course. Okay, so you should be quite fine about here. So, oh wait, let me like leave like this. Sorry, I know that. I know it's very bad when you have just pen and you have to do. Be careful. be patient with me. Okay. So, and this is the power of the chalk. But some people, anyone use the tablet to take. You are very old-fashioned. You can remove a raisin with the tablet. Okay. Okay. So so we have this. We know F and F star, and. One thing that we have to say initially is that when we deal with fluids, we are used to represent the total derivative. Do you remember this? You have are you cold? Everything is closed.
Please, why isn't F star for the U and the Z component, but isn't just F for the V component?
F star. No, it's correct. Why? You.
I'm just asking. F star, F star.
Yes, because from the vector product, you have the sine and the cosine, the two components, omega z and omega y. Omega z is sine F. Omega y is cosine F star. So we must to keep them in our complete equations. We cannot leave them outside. Okay?
And the F alone.
And yes, and here, yeah. You say why two here and one here? It's just because from the vector product. If you try to redo, do you want we do it again? Yes. Okay. So we have this term here, okay? So I know that omega is 0, omega cosine phi, omega sine phi. Because since I am in a okay, this is z and this is y. This is the component z and this is the component y. This is phi, this is phi, and this is phi. This is cosine and this is sine. Okay? So when I do this, 2 e j k, then 0, omega cos phi, omega sin phi, u v w. Okay? So vector product, this is something that you should know, huh? Okay. So I first cosine phi v minus sin phi, sorry, cosine phi w minus sin phi v. Okay? Multiplied by 2, I know that 2 omega cos phi is f star, 2 omega sin phi is f. So this is 2 cosine phi w, so it's f star w minus 2 omega sin phi v, f v. Okay? And the rest is the same. Okay? The only fact that we have 2 here is that because we are looking here, but when we are considering the other 2 components, we always have 0. So that's why we have exactly only 1. Okay. So you should have already seen that how we used to write the total derivative. You remember? One. Raise your hand and speak one. Okay, so how we used to write this?
d dt plus d dx u vector.
Oh, you said? No, you said one very important.
You have to write the advection.
Advection, that's right. So we used to write this. This is the local derivative plus u and then this one, the gradient. Okay? So this is the advection, this is the, so we used to say something, I mean, I'm looking at a fluid. This fluid is moving, so it's transported or advected by the flow. Remember, flow and fluid. So I know that a quantity could be temperature, could be the velocity itself, is changing because of the fact that local is changing, plus because there is the flow which is transporting other information like temperature, salinity, humidity, whatever. Okay, so what we will do here, we will exactly apply the same. So don't hate me. So we will have u, so du dt plus, and then u dxu plus v dyu plus w dzu. Okay, so I expanded all the advection terms. Here the same, dv dt plus u dx, now I'm applying on v, plus v dyv plus w dzv, and finally local derivative of w, u dxw plus v dyw plus w dzw. Okay, so these are the first 3 equations, momentum equations, okay? But I see a problem. Do you see a problem in this equation? Mathematician.
Wait for a while.
Sorry? Yeah, okay, it is a problem as themselves. But if we are like very wide and smart, so what is the problem? How many equations do we have here?
3.
3. How many unknowns? How many?
More than 3.
More than
More than
3.
three.
How many? So we have U,
U,
V, W, and here we are safe. What we have here?
P,
And then?
tau.
No, because tau is function of velocity. You remember? You should remember, huh? What is tau? We will see later, but tau is like stress tensor, so it's only related to velocity. What is the other one? Density. Density. So we have 3 equations and 5 unknowns. So our mathematician friends, and no, not good. So we have U, V, W, P, and rho as unknowns. So we need at least 2 more equations. So which is the equation that we can use? You should have already seen it in the previous course.
Continuity equation.
Continuity equation. Okay, so the continuity equation is quite simple. We can put it here. So continuity equation actually tells you if I have a parcel, if I have something fluid which enters, okay, and density which is changing here, this is done by the fact that I have something entering and something exiting. So there is a source or sink. So usually this is due by the fact that the local variation of density is basically due to the flux of density. Okay? So I'm changing, the balance of mass is due to the fact that locally I'm changing density only if I have a flux of density. Any kind of concentration can be expressed like this. So this can be also written if we express this. So this will be minus, so U gradient of V minus rho U. Okay? So I just apply the gradient term by term. So if I move this on the left-hand side, I will have the local advection, the local time change of density, plus the advection, because this is the advection term. So this will be just the total time change, total time or material derivative of density, which is equal to rho multiplied by the divergence of the velocity. And this can be also written like 1 over rho d rho dt, which is equal to minus divergence. So this is quite fine. We don't have any problem for that because it's something which is general. Doesn't there isn't any problem with rotation. So this is. So we have had we found the fourth equation. So now we need another one at least to finalize. Do you have any hint? Sorry? You were just thinking louder. So we had momentum, we had density, mass. What is the fifth equation?
Energy.
Energy. Okay, energy. So energy, I would need a little bit more space, but I'll try to do that. Okay, allow me to erase this. Then we will rewrite it. So for the energy equation, we will add, we will use the first law of thermodynamics, which says that now this is energy, okay? So this is the variation of the internal energies in a system is due to what? To the heat and to the work, okay? To the mechanical work made on the system. So we will use this and express this delta U, the change of energy, by using the letter E, small, lowercase e, which is the internal energy. Then we will keep Q as the rate of heat, and then we will use the expression which puts the pressure, so the mechanical work is due to the pressure multiplied by the variation of the specific volume. So V, this V here is not the velocity, is 1 over rho. Okay, so the inverse of the density. Okay, so this is something from physics, I mean, nothing new. No rotation, no Coriolis. So we will define E as a function of temperature, where the proportional constant is the heat capacity at constant volume. So heat capacity at constant volume is, for the air, is 718 joule kilogram Kelvin. For the water, seawater is much larger. So just for this, you see that we have like 700, almost 4, so almost 6 times larger the heat capacity for the seawater. Okay, so it means that at the same temperature, since this is expressed for unit mass, okay, so we have 1 kilogram of water or 1 kilogram of air, and 1 kilogram of water has itself 6 times more energy stored than the same for the atmosphere. Okay, so this is extremely important. It's something very small, but extremely important for the regulation of the climate of the ocean for our planet. Okay, so ocean can keep and store much more heat than the atmosphere. So atmosphere is not able to keep the heat, but the ocean is actually like a big storage for the heat. So how we can use Q? So Q, usually we will multiply by rho, and we will simply write the variation of heat as diffusion of temperature. Okay? Because we do not have any kind of source of, let's say, geophysical fluid doesn't have, at least if you calculate, if you want to solve something in the neighborhood of a volcano, okay, you will have a sink, or let's say a source of temperature. But in any case, if you look on the GFD, which is more interested to large-scale phenomena, so you want to say exactly what happened near a volcano, you have that temperature, and we see salinity, are only transported, okay? And in this case, are diffused. So K is called thermal conductivity. And actually, thermal conductivity, the thermal conductivity is, so for the air is 0.02 watt meter Kelvin, while for the water is 0.6. Okay, so this is K air and K sea water. So this is more than, it's 30 30 times larger than this one. Okay, so it means, of course, so water is a better insulation, has a better insulation property than air. Okay, clear. Yeah. Sorry. Yeah, I'm recording. Yes, of course. Yes, it's blinking. Thank you.
We are defining a thermal conductivity, and you are saying it's having a.
Sorry.
The thermal conductivity of water is 0.60, and that of air is 0.02.
2.
So which one has a better insulation than the other?
The water.
So if
The
you have-
thermal conductivity is much smaller. So if you want to transfer, if you have the same variation of temperature, you can transfer the rate of change of heat is much lower for the air than for the water. So I mean, if you put two things, one hot and one warm and one cold, or one hot and one not cold, and you put water inside. Of course, if you put copper, it will be much better. That's why I don't know, no, you don't have this. If you have like the thermos, they are insulated, okay? But if you put like one chamber of air over water, of course you will have a better insulation property in one. Of course, air is good, but water can be much good. Okay, so we can calculate this. So what happened? So we can put this one expression here. So CV is a constant. So we have time variation of temperature. Then we can multiply everything by rho. So we have rho Q. We can use this expression, and then we have minus rho P, and then we have the time derivative of this one. So ddt of 1 over rho is minus 1 over rho squared d rho dt. So this is minus plus 1 over rho squared d rho dt. So rho and rho squared go ahead. And so we have 1 rho d rho dt, which is equal, you remember to what? 1 rho over multiplied by the rho dt.
Gradient of velocity.
So we have divergence. So and this is the energy equation. So we have rho CV dt equal K minus P divergence. So we found the fifth equation, but we have a problem because we have temperature. So we have another unknown. Oh gosh. So we need one more equation. So which is the equation that we need now? So we have velocity, pressure, density, temperature.
No.
Do you have any idea? The one who, those of you who studied meteorology.
Ideal gas equation.
Ideal gas, this is a good hint, but ideal gas is only for air.
Yeah.
So there is, ideal gas is a special form of one equation, which is called equation of state. State. Thank you for your knowledge. We appreciate. Okay, so equation of state. What is equation of state? So equation of state. Actually, sorry.
equals to rho r.
So we usually relate density to pressure and temperature. Okay? So now, up to now, we could consider everything. I mean, the three equations of motion, the momentum, the equation of continuity, the energy equation. We didn't have to think about ocean or atmosphere. Now we have to do it because the equation of state, of course, is very different from ocean atmosphere. So in particular, if we are looking about atmosphere, you were right, because we can say that we can approximate atmosphere to an ideal gas, and saying that rho is equal to pressure over RT, where R is the constant, universal constant of gas, which is heat capacity at constant pressure minus heat capacity at volume, at constant volume, which is equal to 287 meters squared. Meter square Kelvin minus 1. Okay, so for the atmosphere we are fine. Of course, this is a very big approximation because this give us the opportunity to consider only dry air. But what is the important property of the air when it is not dry? What do you say?
Water vapor.
Water vapor.
Water vapor.
Ah, water vapor. Water vapor, yes. Water vapor, and water vapor is made by, I mean, what is the water vapor is something, is a phenomenon, but which is the variable, the quantity? Wait, one question at all. Humidity.
Okay.
Okay, moisture, yes, sure. So, humidity, so we use Q, and so we will have one more unknown, and we will need to have an equation of humidity, okay? So in the first approximation, we can say that humidity is, we can use a sort of diffusion of humidity, okay? Of course, this is not enough, but we can use it for now. So what happened to the ocean? So in the ocean, we can say that density increase when we have, sorry, you had the question? Okay. So we can say that density increase when we have cold water, or decrease when we have hot, warm water, okay? And also density increase when we have salt, right? Because in the ocean we have salt. So if in the atmosphere we have humidity as an important tracer, we have salt, salinity in the ocean. So what we use is this equation of state for the ocean, which is a linear, in first approximation, a linear dependency between the value of density, the reference value, rho 0. Then we have variation in temperature multiplied by a coefficient of thermal expansion, and variation of salinity multiplied by a coefficient of saline contraction. And these two are very small, so alpha is order 10 to the minus 4 Kelvin to the minus 1, and beta, I think, is the same. Yes. Sorry? Contraction.
Is this
Yes.
Q?
This one?
Yes.
Yes.
For what is it? Is
Humidity.
The QDT is equals to
QDT. So it is because since we have, okay, for the dry air we are fine here. But since we have moist air, when we have moist air, which is the most general case, we need to add also humidity. So humidity is one unknown more that we have to add to our system. So for the moment we can say in order not to be crazy, to say that the variation of the evolution of humidity in time is simply due to a diffusion. Okay, so just Laplacian of humidity. Okay, with a certain constant of diffusion of humidity. Okay.
Okay.
Alpha and beta, are they equivalent in magnitude?
Alpha and beta, they are equivalent, yes. But this is Kelvin minus 1. So this is actually is
10 to the power, what's beta? 10 to the power?
is alpha, okay, 1.7 10 to the minus 4, and beta is 7.6 10 to the minus 4. So this doesn't have any unit of measure because salinity is without unit of measure. We in the past people use PSU, practical salinity unit, but since salinity is actually how much salt you have in 1 kilogram of water, so usually we say grams over kilograms. Okay? And usually we have like 35, 38 something grams over 1 kilogram of water. Okay, so this is the salinity. And very small, very tiny, so moving from 35 to 38 is huge. If you look at the map of salinity surface in the global ocean, you will see that salinity varies very, very, very few. Very, very, very small. So we used to have like a value of reference value. Indeed,
1.7 times 10 to the minus 4.
minus 4. And this is 7.6 10 to the minus 4.
Okay.
Okay? 4, 4. Minus 4, minus 4. Then we have rho 0. So rho 0 is the background density, 1028 kilograms per cube meter. T0 is 10 degree. And S0 is 35. Okay? So, of course, this equation here is empirical. So you will find it as a standard, which is usually called UNESCO. Okay? So all the oceanographers meet sometimes, and they say, okay, I want to change alpha. I want to add, let's say, some, I mean, it's a polynomial, of course. So it's something that you can take like thousands of measurements of temperature, thousands of measures of salinity, you put together, you calculate the density, and then you find an expression. So it's something that, this is the very first approximation, but it's good for our purposes. If you look if you Google, you look for UNESCO density seawater, and you will find something, which is similar also for the humidity.
UNESCO what?
Sorry? UNESCO is what we call it the standard for the equation of state of seawater. Okay. So we had like 1, 2, 3, 4, 5, 6,
7.
and 7. And of course we need also something for salinity. What we can do. So again, we will find a very, let's say, conservative solution, and
Sam, what's our objective? I forgot.
you need more coffee, huh? So we started to define the equations. Okay? So we started to find the equation. We want to find how to describe the GFD equations. So we started from the equation of Navier-Stokes for the fluid dynamics. Then we said that Navier-Stokes in fluid dynamics must be changed in geophysical fluid dynamics because we have rotation. So we found Coriolis. After Coriolis, we said, okay, now we start to go deeper and find which are the equations. So the Navier-Stokes equation has 3 components because it's momentum equation, U, V, W. And then we started from the first 3. But in the 3 momentum equation, we had 5 unknowns. And so we are starting to, and now, but we are finished. Be safe, okay?
Sir, can you kindly be writing the headings anytime we are going into one section so that...
Going like this? I will do my best.
Also the salinity, is it 35 or 3 grams?
35.
Okay.
I said before, 35. So this is a reference value.
Then the unit has to
There
be
is no unit.
Gram per kilogram is
Yes, exactly. But usually it is without units. So if you like, you can use PSU, which is practical salinity unit, but it's deprecated. So actually, people don't use.
You said, I'm sorry, beta is saline contraction. I just need the word.
Yeah, but don't worry. I mean, it's important that you don't.
Understand.
You are losing in details. Don't lose details. I mean, that is a good question. Even if you are a little bit, you need some coffee maybe. we can take some break if you like. But no, I mean that is good. But the name of the constant. I mean, you can find it also on the book. Okay.
Okay.
So, and it's not important. I mean, it's important only to understand that they are very small. As we will see later, they are very small. Okay, so just to have the idea, for the seawater, we wanted to arrive here. So, continuity of mass. So you are going to make solid dirt or climate?
No, climate.
You know how they do when they play football, no, Amber? Okay. So let's try to because everything is recorded, so don't want to. Let's give some more serious to the lecture. Okay. So continuity. Then we have the 3 momentum with the Coriolis, the pressure gradient, the stress tensor, and for the vertical one we have the body force. Then we have the equation of state, the equation of energy, and the equation of salinity. Fine. Air. The same up to here. Then we have ideal gas for the dry air, energy, and humidity. What happens usually is that people working in for the atmosphere use not the temperature but the potential temperature, okay, which is a little bit weird to be found, but is actually a function of temperature and depends on density and on the constant, universal constant of gas. And so you can rewrite the equation of energy as the equation of, which is actually the equation of temperature, in the equation of potential temperature, which again is has a diffusion form, okay? With the only difference that we have this term here where we have temperature and potential temperature. Okay, so fine. I would say we are nice, we are happy, but can we solve these equations? Yeah, numerically, sure. Analytically, not. So since we are going to, people are going to work with this equation because in any case, all these equations have time variation. So we want to actually forecast what happened. So we can solve, we have initial condition, we can say what will happen to tomorrow, what will happen in 2 days, what will happen in 2 weeks, and in the future projection. So we are able numerically to integrate this equation, but they are very difficult. So in the history of GFD, people start to use the approximation. So approximation are extremely important, and they are in some sense inherited by engineering, because the idea is to highlight which are the most important terms. So I'm able to neglect some of these terms and solve, let's say, a reduced form of this equation? Actually, yes. So one of the first, let's say, the first approximation that we can do is the one which was inspired by the work of Boussinesq, which was a French mathematician and physicist. And he was smart. He said, well, density differences in the atmosphere and in the ocean are sufficiently small to be neglected, except when multiplied by gravity acceleration. So we can express the field, the density field, as the sum of a background density plus a perturbation, rho prime, where the density is a constant, can be 1.2 kilogram per cubic meter in the atmosphere or 1028 kilogram per cubic meter in the ocean, and this is a function of the position and time. But rho prime is much smaller than rho zero. So provided that rho prime is not multiplied by g, because if it is multiplied by g, we have something which is rho prime g. So this is the buoyancy. So this is extremely important. If you neglect this, you lose a lot of dynamics. So if we do this and we start from the mass equation, which is actually the equation which deals with density, so what we have is, so the rho dt plus divergence of the mass flux. So we can start to substitute rho as the sum of rho zero and rho prime. So if I am here, so d rho dt, since rho zero is a constant, so what I obtain is simply d rho prime dt. So I'm just considering not the time variation of density of the background density because it's a constant, but only the one of the density perturbation. Then I can do the same here. So I will have rho zero plus rho prime divergence plus u, and then the divergence will be applied to rho, but again I will only have rho prime. So I can express this one, so I will have rho zero delta u plus rho prime divergence. Okay, so I have four terms.
Sir, can you come again with the explanation why you are taking the time derivative of rho prime instead of the rho?
So I just take rho, which is equal to rho zero plus rho prime. So when I do the time derivative of rho zero, that is zero, because rho zero is a constant. Okay, so the only term which remained is rho prime. So in order to go ahead, we have to say that in GFD, the variation, general variation of density with respect to the density are much smaller than the relative variation of u, of the velocity. So this means that density change much less than velocity. Okay? So this is an hypothesis that we can also look from the we can also see from the equation of state. So if we take the equation of state for the seawater, for example, okay, let's concentrate only on the variation of temperature. Okay, so this simply say that density increase when temperature is decreasing because of the minus, and decrease when the temperature is increasing. So I can express this, so I have rho equal to rho 0 minus alpha rho 0 T minus T0, so I can put this on the other side. And so I can divide by this. And so this is rho minus rho 0 divided by rho 0. So these are variation of densities, which is equal to minus alpha variation of temperature. Okay? So this variation of temperature in GFD, let's say in the ocean and also in the atmosphere, they are delta T, they are order of 10. Okay, so we can have temperature from -5, -10 to 10, 20, 30, but we cannot have never 100 of temperature. And in the ocean even less. The range of temperature is this one. So alpha, as we said before, was 10 to the -4, okay? So if we have 10 to the -4 multiplied by 10, we will have that all this term here is 10 to the -3, okay? So it means that in GFD, in atmosphere and the ocean, we can expect that variation of density will be order of 1 per 1,000 with respect to the background density, okay? Which is exactly what the Bosniak's approximation say. So if we extend this and we consider the variation of velocity with respect to the velocity, this will be much larger than this one, okay? So if we take how much velocity change, the variation of velocity is extremely large, okay? So
variation in density will give you the pressure gradient, and then that can create large velocity of any mass of fluid. So why are we saying that?
So this is something, okay, this is, if you take a ratio between the variation of density to density, is a pure number, okay? So I'm just saying, how is the relative change of the variation of density, how is the relative change of variation of velocity? No other no other arguments about this, okay? So this, which is an experimental evidence, give me the opportunity to come back to the mass continuity, to the continuity equation, and say that if I'm going to compare this term with this term, I have that rho 0 is much larger than rho prime. So I can neglect this term with respect to this term. Okay? And if I, again, compare this term to this term or to this term, so these two terms are variation of density in time and in space. But we have said that variation of density is much smaller than variation of velocity. So these two terms actually can be neglected. Of course, this is an approximation, okay? It's not exactly 0. So I'm taking a sort of scale analysis. So which is the dominant term in this equation? So it appears that the dominant term is this one. So from our consideration, we can say that if we consider the Bosniak's approximation, the continuity equation or the conservation of mass transform in this condition, which is the incompressibility. So fluids are incompressible according to Boussinesq.
You come here for
This one, again. So, I have 4 terms. This term here, rho 0 multiplied by divergence, is much larger than rho prime multiplied by divergence, because rho prime is much smaller than rho 0. So I can say that this one is much smaller than this one. If I compare this term with this and this, I know that the variation of density are much smaller than the variation of velocity. So here I have variation of density in time and the variation of density in space. So these two are much smaller than this one, which is variation of velocity. This is an experimental evidence. So it's exactly when we said we will say that if we take our planet and we will consider the GFD motions, we will have that the horizontal scale is much larger than the horizontal scale is much larger than the vertical scale. Okay? So all the phenomena are occurring on a very small peel, let's say. So the typical vertical scale for the atmosphere and the ocean is, let's say, few kilometers with respect to the whole radius of the Earth. And if we consider this scale with the horizontal scale of the phenomena, which we have seen can be like thousands of kilometers, this is like the horizontal scale is much larger than the vertical one. So this is something similar. Okay? Would you like to take a break?
Yes.
For a few? Okay.
Thank you.
Okay. Good. Okay, so we started from the conservation of mass and we obtained the conservation of volume. Okay? So this actually say that if your divergence is 0, so you have that flows are always convergence or divergence free. Okay? So, and this means that you have uncompressibility of the flows. And another important implication is that you don't have any sound waves, because sound waves are due to change in exactly.
Sir, one question. How can we distinguish? Because for if the flow is steady, then even we have divergence of that V is 0, yeah? From the continuity equation.
Yeah.
So for both of these cases, so the divergence of V is 0, how can we know which one is the effective cause?
Which one you mean about this and this one? So this is always true, okay? But if we apply the approximation, the Boussinesq approximation, we have that these terms here are much smaller than this one, okay? So we cannot say that, I mean, both are true, even if exactly, in steady. I mean, this means that you don't have any change of pressure because of density, because density remain constant. Okay? So, or at least the conservation of mass doesn't deal with variation in time of density. Okay? But only in variation of velocity in space. Okay?
So incompressible means constant density over the space, yeah?
Yeah. So if you have a parcel, If you want to change the density here, you can do only to the fact that you have divergence of flow. So you are putting here the fluid, but since you have this, so the divergence is free, you must have a conservation of the divergence. So if I express this is dxu plus dy plus dZw. So mass conservation for a Boussinesq fluid means that these three terms must be balanced, even if I am in steady or not steady condition. And we will want to say exactly what happened to this expression. So we will look at it later when we will start to make further approximation, but I will leave it there. Okay. So now we want to say what happened to the if we apply the Boussinesq approximation to the momentum equation. So the momentum equation, you remember, had like rho here in front of the left-hand side. So if we substitute rho with rho 0 plus rho prime, we have that rho 0 is much larger than rho prime. So we just remain here with rho 0. Okay? So there is no prime in the left-hand side. If we go here, we have now to look what happened to the stress tensor, and then we will have to analyze this term here, which is the most important one for the Boussinesq approximation. So let's take, for example, the first, the x component. So we will have, so we said rho 0. So we have du dt plus f star w minus fd, which is equal to minus dp dx. Okay, tau x6, tau xy, tau xz. So do you remember which is the expression of tau? So tau ej is mu di uj plus dj ui.
Constitution equation.
Sorry?
Constitution equation.
Constitution equation. Okay, I never heard about it. I know that like the stress tensor equation, but it's okay. So mu, do you remember mu? What is?
Viscosity.
Viscosity.
Static.
Static. Still static. Coefficient of
Static.
dynamic viscosity. Then when we have mu over rho 0, which we will call mu is kinematic viscosity. Okay? So what we will use mostly will be this one, the kinematic viscosity, which is larger in air than in the seawater. Okay? Then we will see the numbers. Okay, so let's try to work on this. So tau x6. So we have the x tau x6. So this will be plus the x. Tau x6 x mu the xu plus the xu. Then we have the y mu, so is xy, so it's tau x v plus dy u. And then we have the z mu the xw plus the zu. Okay? So we can rewrite it by taking the constant out, putting everything together. So we have the x, the xu, then we have the y, the yu, and then we have dz, dzu. So we have second derivative in x of u, second derivative in y of u, and second derivative of z in u.
So Laplacian.
So we can write it, we have Laplacian of u. Then we have the x, the xu, the y, the xv, and the z, the xv. So we can put everything in the x. Since they are independent, we can change the order of derivation. And so we will have dxu plus dyv plus dzw. Right? So what is this?
Divergence.
Which is 0. So the Bose-Nex approximation strongly reduces the stress term in our momentum equation, which basically is related to the surface forces, only to the Laplacian of the component. So we will have for the velocity, for the u component, we will have just this. So I can oh, come on. Okay, I will write it again. So this was again the x. Okay. So for this term, we will just remain with this one. For the v component, we will have minus dp dy plus mu Laplacian of v. And for the z component, we will have minus dp dz plus mu Laplacian of w. And then we have minus, then we have rho g. So we have rho 0 plus rho prime g. Okay, so the vertical component is very specific because we have pressure. And since we want to see how the pressure change in the vertical, we have to take in account, what you mean what? The hydrostatic pressure. Okay, so hydrostatic pressure is simply so the variation of pressure in the vertical is equal to minus rho 0 by g. Okay? So this is because, in particular, we can do the same trick that we did with the density, with the pressure. So we will write that pressure will be P0 plus P prime so we can separate the effect of hydrostatic pressure by all the other effects which are not related to the hydrostatic. Okay, hydrostatic is static, so it's anything related only to the static, to the fact that any fluid has a weight, and so it exerts a pressure over the other, let's say, parcel of fluid which are above, below itself. So we can have the hydrostatic pressure, which is this one, and then the other one, which is the perturbation pressure, or also dynamic pressure. Okay? So we solve this equation quite easily. So if we integrate over dz, so what we will obtain, so we will have integration of dp0 equal to minus rho 0 g dz. So this is between 0 and z, and this is between a certain p0 capital to the value of the hydrostatic pressure at certain height z. Okay? So from this, I can solve Pz, the hydrostatic pressure, which is equal to a reference pressure minus rho 0 g z.
Exponential.
Why exponential?
Oh no,
Linear, everything is linear. Because the change is constant. Okay, so we can use this, which is solved, clear, easy, and put it here. So when we do this change in our expression of P, what we have, allow me now to cancel here. So this term here, so we will have dp dz, which is equal to d p0 plus p prime over dz, which is, now this is derivative, partial derivative, but p0 only depends on z. So I can use total derivative plus partial over z. Because, why partial? Because p prime depends also on x, y, and t in most general case. So now I can solve dp0 dz, which is this one. So this is minus rho 0 g plus dz p prime. So now I can put everything inside. So I have a minus here, so I will have rho 0 g minus dz p prime, then I will have this one, and then I will have minus rho 0 g minus rho prime g. So these two terms can be neglected, and I obtain the variation in z of the dynamic pressure and the buoyancy term, which, as we expected, is the only point in all the equations where the perturbation density appears. But it's the most important because it's the buoyancy term, because it's multiplied by g, except when multiplied by a gravity acceleration. Okay, so we have also the third equation. What happened now to, so we did the mass equation converted to a divergence spring. We found we had a simplification of the stress term, and we obtained only the Laplacian in the horizontal components. Then we also have an argument relating to the hydrostatic pressure, and we found the buoyancy term in the vertical component of the momentum. Now we need also to deal with the energy equation. So density equation, let's take, for example, this one. So density equation, we can look at it here. So rho CV dt dt plus P
Divergence.
So no longer this one. So we just remain with rho CV dt dt equal, stop. So we just reduced it to a very similar equation for the diffusion of temperature. We can even rewrite this and define a new quantity, which is kT over, this is rho 0, of course, because, don't forget, sorry, I just changed this rho as rho 0 plus rho prime. Rho prime is much smaller, so we just obtain rho 0. So we have rho 0 CV, so this is heat diffusivity, okay? Because we are talking about diffusion. So what we obtain is simply an equation of temperature which is simply related by diffusion of temperature. Okay, so temperature evolve only due to diffusion law, no more. Of course, here we must consider that we have also advection. Don't forget it, because here we also have still a local variation of temperature plus advection term. Okay, but what we are having on the right hand side is a simple form of diffusion, which, by the way, is similar, as we also say, isomorphic to the salinity equation. You remember? We talked about before. Okay? So the energy equation, so the continuity equation turned into a divergence-free equation. The energy equation turned into a temperature equation, which for the seawater is isomorphic to the salinity, and for the atmosphere is isomorphic to the humidity. So everything seems pretty interesting. The nice thing is that for GFD, since we are dealing with scales which are larger, so this K here, let's say larger, of course, the horizontal scale will be much larger than 1 meter, okay? So over this large scale, we can safely consider that the diffusivity, I mean the one related to temperature and the one related to salinity, are of the same order of magnitude. And we usually also to write them like simply K, which is 10 to the minus 2 square meter to the second. Okay? So don't be lost in this. Just consider that for seawater, when we are dealing with the motions larger than 1 meter, which is of course the subject of GFD, we can safely consider that the diffusion is acting not just on the molecular scale, okay, but on what we call the eddy scale. Okay, that's why we call it eddy diffusivity. Okay, so eddy diffusivity is related to turbulence, and it means
you said K, big K is KT, I will not see.
this one.
Yes.
Mm-hmm.
Then it was just K, but then
Yeah.
and I'm confused.
Let's say that this is for temperature and this is for salinity. Yes, thank you.
Okay.
So this is related to thermal diffusion, this is related to saline diffusion. But this, I mean, in first approximation, these are related to the molecular diffusion, but since molecular diffusion in GFD, we don't care about it. We are interested to very large phenomena. So we can consider that KT and KS, which usually are different because KS for the molecular. So if you take one parcel of seawater, you will find that the saline diffusion is much slower than the thermal diffusion. Okay? So, and this is a phenomenon called double diffusion. Any of you already know about that? Double diffusion? No? Okay, no worry. Maybe if we will have time, we will talk about at the end. But it means that due to the fact that salt diffuses much less efficiently than temperature, you have difference in these two numbers. But since this is only for small scale, since we are interested in large scale, we can consider this like same. So salt and temperature diffuse with the same velocity. And we call this the eddy diffusivity, because all the transfer of information, and this information is related to the properties of the fluid, temperature, humidity, salinity, is ruled by eddies. So eddies are vortexes. Okay, so inside the flow we have many different vortices which transform and transfer the properties of the fluids. Okay, and we used to let's say call this diffusion related to ruled by the eddy diffusivity, which has this value here, which is actually much larger than the one of the related to the molecular scale. So in some sense, turbulence is much more efficient to transfer properties in the flows than the molecular. So it's exactly, if you take one candle, you switch on the candle, and you wait that the heat is transferred to one room, it will take hours and hours. Okay? So if you, because without any kind of, let's say a candle maybe is a little bit small, but if you use the radiator, we don't have a radiator here, but if you have a source of heat and you have any kind of convection in your room, the transfer of heat will be very slow, very not so efficient. That's why usually people put the radiator close to the window, because the window is the less, the colder part of the room. So if I put a source of heat close to a colder area, I will create some convection, and so through the convection I will irradiate and heat the whole room. Okay? So otherwise, if I don't have any kind of mechanical forcing, which is related to convection, I won't have any kind of, the transfer of heat will be much, much slower. Okay, so we move to energy, to temperature, and now we can, yes, we can still make one step ahead. And
for the temperature, I'm not seeing well. K is equal to KT over rho, or KT is equal to K over rho.
so we start from the equation before. That KT, we call it thermal conductivity. Okay. Then when we use the Boussinesq's approximation, we can rewrite this equation and use it just one single constant. It's just a matter of constant. So is no, these are just numbers that you have for any fluid. So you have the KT for the air, for example, rho 0, and CV for the air, or different for the seawater. So I can use this and rewrite this equation, and I will have 1K related to the temperature and 1K related to the salt, because these are different. One is for the air, for example, one is for the water. Okay? So I will have the salt and let's say air or water are different. I mean, air is a fluid, salt is solid. So you can have that salt diffuse in a different way from air or water. That's why we have this phenomena in the ocean, which is called double diffusion. Okay, so these two, if we consider larger scale motion, these two can be considered equal because the way how temperature and salinity evolve in time with respect to the diffusion of temperature and salinity is more or less the same and is related to eddy. So it's the eddy which are related to turbulence, which transfer the properties, and in this case transfer temperature and salinity in the medium. And an approximation and a number that is often used is 10 to the minus 2 square meter over second. Okay, so we were able to approximate, to simplify some equation, but we can do a little bit more. And if we look at the typical scales of atmospheric and oceanic flows, if you remember, we gave to each variable a scale. So for the horizontal length, x and y, we have the capital L, which has a unit meter, and we have 100 kilometer for the atmosphere and 10 kilometer for the ocean. Okay? You remember when we did at the beginning of the second lesson, we found this natural scale by the fact that stratification. Okay, so more or less these are the order. No, we had the cyclone, let's say, which was like 500 kilometers, and the ocean eddies, which were about 60 kilometers and so on. So what about the vertical scale? The vertical scale is 1 kilometer for the atmosphere, 100 meter for the ocean. You see there are, let's say, 1 order of magnitude between atmosphere and ocean, and 2 order of magnitude between the horizontal and the vertical scale. So this is the first thing that we must consider, the fact that, as we anticipated before, GFD is interested in large scale motion with L much larger than H, and we consider time scale larger or order of 1 over omega, which is 24 hours. Okay? So we have for the atmosphere more or less half a day, and 1 day for the ocean. Of course, this is an approximation. Then we have the horizontal velocity, which is 10 meters per second in the atmosphere, 10 centimeters per second in the ocean. Then we have various, let's say, vertical velocity is extremely low, extremely small, as we will see. Then we have pressure, which is variable, and density variation, which is 1% of rho 0 and 0.1% of rho 0 for, respectively, atmosphere and the ocean. Okay, on this base, we will see what happened in the equation in the next lecture. Okay? So these are the hypotheses where we will build a further simplification of our equation based on the typical scales of motion.